Well, greetings from the other side of the pond, as they say in England. I don't know if you say that here. But anyway, I'm going to be talking about a field of study that I've been working on for 20, 25 years, and that's in the field of geomorphology. Geo means earth, morphology means shape, so it's the shape of the earth, and I discovered quite a few mysteries on there, mysteries to the secular view, but can be explained readily with the runoff of the floodwaters. So I'm only going to share a few of these with you today. So my title of my talk is Earth's Surface Shaped by Receding Floodwaters. Now there's many claims that there's no evidence for the Genesis flood. For instance, this claim by Dr. Davis Young, retired professor of geology at Calvin College, says there is no geological evidence to confirm the idea of a universal deluge. So when you hear statements like this, both within and outside the church, it makes you wonder, what is the Bible describes a universal flood? So is the Bible wrong? How should we respond to this? Well, this is my theme verse for all research. Examine everything carefully. Hold fast that which is good. I'm going to hold fast to the Bible as God's word, His communication. I had to learn that. I was raised in a liberal church that said there's a lot of errors, but I checked it out for myself, trying to be open-minded, and I discovered, hey, these made sense, unlike what I was taught. But when you hold fast the Bible, this verse says you got to examine everything carefully. We have a problem today of just accepting what we read in the news, and we don't check things deep enough. And you have to dig below the superficial level. And that's what you need to do with many of these. And sometimes it takes years for any one issue. But we need to do this. And this is what I've been doing in geomorphology, as well as the Ice Age for many years. Now this is erosion by climate and surface topography in 5,000 years, the flood being about 5,000 years. This tells us how much erosion on the average, or in big broad areas, by the way, in 5,000 years. So you can see that the highest is, if my cursor can show this, yes, that mountainous areas with high precipitation in 5,000 years have eroded about an average of 7 feet, and translated to meters, that's a little more than 2 meters. So with that amount of erosion, assuming the same amount of precipitation all through that 5,000 years, there's been very little erosion. Well, what's the point of this? The point is that if the flood was a real event and it ran off, the last event was the runoff, we should see the evidence of the flood on the surface of the earth if the flood was a real event, because there's been too little erosion to erode these features, and indeed we do. But before we talk about the features on the surface of the earth, we need to answer a few questions. 2 questions. How did the floodwater drain off the future continents? And secondly, these features I'm going to show you are due to erosion. So and rapid erosion. So do we have evidence of rapid erosion? So I'm going to be dealing with these questions first. So how did the floodwaters drain off the future continents? I believe it's in Psalm 104, verses 6 to 9. It says, "You," that's God, "covered it," that's the earth, "with the deep as with a garment. The waters were standing above the mountains." Now, notice that the word "covered" there. Some people think that these verses apply to Genesis the third day of creation, and when the earth was totally flooded. That's the only other time it was totally flooded by the waters below. But that period was an uncovering. The dry land appeared, and an uncovering. This is a covering, so it's definitely referring to the Genesis flood. At your rebuke, they fled away. In other words, God was in charge of the flood. At the sound of your thunder, they hurried away. That's the water. The mountains rose, the valleys sank down to the place which you established them. You set a boundary that they may not pass over, so that they will not return to cover the earth. In other words, God set a boundary so the waters wouldn't cover the earth again, indicating, again, this is referring to the flood. But notice verse 8 there. The mountains rose, the valleys sank down. Well, when that happens, the water is going to be draining. It's if you're on the part going up, you're going to see the water's draining. So that will help. That will drain the earth. So here's the big picture of the draining floodwaters. About day 150, around the peak of the flood, you had wide currents moving across the earth, like this right here. Maybe about 2,000 kilometers wide, and moving sort of like the jet stream in the atmosphere that I've studied. So as wide flows, and then they transformed to more channelized flow, and the land came up, and the water, like this is the western U.S. right here. This big, large scale, maybe 2,000 kilometers wide, and it divides the water, start running off the land as the land is coming up. And when they're moving off the land at sometimes high speeds, they will erode rapidly and cause all kinds of unique features on the surface of the earth that when we drive around the surface of the earth that we can see. So is there evidence in geology that the mountains rose and the valleys sank down? Yes, it's actually all over the earth, even on the ocean bottoms, as I will get into. You can see it really well where I live. I live here's Yellowstone Park. I live about right there in Montana. And the state of Wyoming is a series of mountain uplifts and sinking valleys and basins that filled up with sedimentary rocks. And here you can see the change really well. For instance, in the Beartooth Mountains, by the way, there was evidence that at the peak of the flood, the upper crust, the granites, were generally level with sedimentary rocks on top of them. We know that from a number of indications from geology. Erosional remnants at the tops of mountains of sedimentary rocks like this one right here, the Beartooth Butte. That's 1,600 feet of mostly limestone as an erosional remnant. Anyway, we're looking at what's called the Beartooth Mountains, and then we have the Bighorn Basin, and then the Bighorn Mountains right in here. This pattern is granite of the upper crust, and it was once flat over it, but now this is up to about 4,000 meters above sea level. Same with over here. But the granite in the Bighorn Basin is about 3,000 meters below sea level, indicating a change here of about 7,000 meters, where this went up and this went down. And in this case, it was at a fault, the Beartooth Fault. And then the basin, which is about 120 kilometers wide and about 180 kilometers long, filled up with sediment. So all this happened underwater during the time of the Genesis flood. But the change is about, what did I say, about 7,000 meters. But you go to other basins and mountains in Wyoming, and it's even more than that. The highest mountains in Wyoming are the Wind River Mountains. This is about, 4,500 meters. And then the lowest basin where the crust is dropped is the Little Hanna Basin right here at about 10,000 meters below sea level. So the difference between the Wind River Mountains and the Hanna Basins is about 14,000 meters, changed like this, showing huge, what we call differential vertical tectonics, where the mountains rose and the valley sank down, filling up with sedimentary rocks, or mostly filling up with sedimentary rocks. And I believe it happened on the large scale, where the future continents, right in here, everything was covered, but the future continents were rising and the future ocean basins were sinking. So at the end of the flood, day 370 approximately, the continents were exposed and the ocean basins sunk. And that all drains the floodwaters into the current oceans. So we have a lot of evidence for that. In fact, way out in the ocean, there's a number of evidences for the sinking of the ocean basins, but one of them out far from land is what's called guyotes. Right here, this is a seamount, or sometimes it's actually a plateau, a large plateau. They've been sheared flat. A lot of these are volcanoes, and they've been sheared flat, and this probably happened at sea level. But the average guyot right now is about 1,700 meters below sea level. So it indicates that the ocean bottom is sunk around an average of 1,700 meters. And Dr. Lester King, a geomorphologist from the University of Natal in South Africa, who's been a world traveler and has studied these features all over the earth. I have more quotes from him later, but he says, marine volcanic islands which have been truncated by the waves and since subsided below sea level are called guyotes. Most of them seem to have sunk by 600 to 2,000 meters, and it is evident that they afford a measure of the amount by which the ocean floor has sunk in later geological time. Now, that later geological time would correspond, in our time scale, to the time when the floodwaters were draining late in the flood. He goes on to say the Pacific floor has especially subsided. All the ocean basins afford evidence of subsidence amounting to hundreds and even thousands of meters in areas far from land. He goes on to say, notice the adjectives he uses. So the fundamental tectonic movement of global geology, notice this is global geology, not just local geology, are vertical, up or down. Every part of the globe, on the continents or in the ocean basins, provide direct, notice that, direct, not indirect, direct geological evidence that formerly it stood at different levels, up or down. Now this is a difficult quote, mainly because a lot of scientists can't write well, including myself, but he's essentially saying that we see it like this now, but the evidence was that it was like this in the past. So everything's moved vertically, up or down, all over the globe, on the ocean bottom as well as on the continent. So there's a lot of evidence for this mountains going up and the valleys going down. In fact, Lester King practically quotes Psalm 104:8, saying there have always been repeated tectonic episodes, always in the same sense. The land goes up, the seafloor goes down. There's tremendous evidence for differential vertical tectonics that drain the floodwaters. So just like Psalm 104:8 says, and what geology says, that because of this differential vertical tectonics, the floodwaters drain. And when they drain, they're moving off at sometimes high speed. So the second question is, in geomorphology, which is the result of erosion of the continents, is there evidence for huge rapid erosion of the continents? Actually, there is. It's abundant on all the continents. Now, here's the southwest United States. This is the Colorado Plateau, right in here. This is an area of about 220 square kilometers, and it's color-coded. The low here, well, you can't read that, but these are low areas in here, and in the Colorado Plateau, which is generally a high area, the blues are low, while the greens and browns are high, and these colors are especially high. These are the southern Rocky Mountains that go up to about over 4,000 meters. But this is the Colorado Plateau. But on that plateau, we've had some domes rise, and these domes have been eroded. That's how you can tell the amount of erosion in many places, by erosional remnants and eroded domes that have uplifted, and the center has been eroded. Here's in the northwest Colorado Plateau. Right in here is the San Rafael Swell. It's a dome that rose and was eroded all through in here, and leaving dipping strata, sedimentary rocks, dipping to the north about 6 to 8 degrees. And I did a rough calculation of the amount of erosion over price in this town called Helper, right in this area right in here along the north edge of the San Rafael Swell, based on the dipping strata and the distance by trigonometry and by erosional remnants up here. This is the amount of erosion I got 4,200 to 5,100 meters. That's huge erosion over the, and by the way, the top formation is the Green River Formation, which some creation scientists think is from a post-flood lake, but in this situation, I don't see how that interpretation can be possible. From the journal Earth Surface Processes and Landforms, it is stated that taken overall, the mean thickness of the sedimentary cover removed from the Colorado Plateau lies between 2,500 to 5,000 meters. That's the average. That's a huge amount of erosion. And we can calculate it because of these domes that rose up. But we can calculate it other areas by a lot of times trigonometric methods. Here's just a few figures from the literature. The Rocky Mountains and foothills of southern Canada, 6,500 feet. I'll just do this in feet. 21,000 feet for the Appalachian Mountains. I've actually done a calculation on this and actually verified this calculation here. 20,000 feet, Flinders Range, South Australia. 10,000 feet, the Welsh Mountains of the United Kingdom. 5,000 feet, Southeast England. 8,000 feet, Southern Africa. So the point is the continents are greatly eroded. I've estimated maybe an average of around maybe a kilometer well, actually there's about 2 kilometers of sedimentary rocks on average on the continents. And I've estimated maybe an average of about 600 meters has been taken off. In fact, here's kind of a block diagram that shows this. Here's the current continental sedimentary rocks. Some places very thick. And of course, you find a lot of fossils on the surface. This is the current continental surface. But we have evidence that at one time, the surface of the continent was much higher. In fact, this, I believe, is approximately at the peak of the flood, day 150, because after day 150, the water started to recede, and that's when you had your massive erosion. And so it's called the retreating stage erosion. Was this much erosion? It's called the Erodozoic. As the late Roy Holt has pointed out. There's also evidence that the erosion occurred rapidly because during this massive erosion of the continents, it left behind erosional remnants that give you a clue how fast it occurred. This is a field in South Africa that was eroded by a flash flood. And as you can see, it eroded this whole area in here, but it left a few erosional remnants that weren't eroded, like this tall one right here, and these small ones in here. So floods leave erosional remnants. So we can see these erosional remnants from the flood, the Genesis flood, the global flood, all over the earth. My favorite is called Devil's Tower, northeast Wyoming. And this one especially shows the amount of erosion. This is the throat of a volcano. Just think of a volcano going way up in the air, up into here. And this is the remnant of the throat. And lava doesn't go up through air, but it had to go up through sedimentary rocks. So the sedimentary rocks were at least above here. Now the secular scientists think the sedimentary rocks are about here. This tower is about 300 meters high. So the sedimentary rocks are probably, they believe, and I think they're correct, around maybe 1,500 meters higher. But during the erosion process, all that sedimentary rock was eroded, but left this tower hanging vertically. Now erosion on vertical faces is much faster than on horizontal surfaces. So there's no way that this can be sticking up for millions of years because it would have eroded long ago. In fact, they used to say that the tower now is filled with cracks, and in those cracks you get water that freezes and expands, and it will knock off the blocks of rock. So this Devil's Tower cannot last more than maybe 10,000 to 100,000 years. It's very young, but they used to say in a road sign that the sedimentary rocks eroded to this point. 40 million years ago, the sedimentary rocks are right here. So in 40 million years, all the sedimentary rocks eroded all around this, leaving this vertical face full of cracks. That makes no sense from present-day erosion, the way erosion works. That should be a pile of blocks in like I said, 10,000, maybe a maximum of 100,000 years. So the only way you can account for this is rapid erosion that leaves a few erosional remnants behind, and it hasn't had time to collapse. In fact, the width of it hasn't hardly changed, and yet it's been the same width over millions of years. And there's a lack of what's called talus at the bottom of it for those millions of years. This is a young feature. And the only way you can explain it still standing is by rapid erosion of the whole plains area, leaving erosional remnants. And this is maybe a unique feature, but you see these erosional remnants all over the earth. For instance, here's another one. Massive erosion of the surface like this. And there you go. There's some more erosional remnants seen around Monument Valley, Utah. And then where did all the erosional material go? Well, remember, at this point, you had wide currents moving off. And so you'd erode and you'd deposit the material where currents slowed down. They will slow down when they reach deep water, which would be the edge of the continents, which were sinking. You have evidence that they sank thousands of meters, and it would fill up these areas where it was sinking on the edge, forming the continental margin, which is composed of the continental shelf, continental slope, and the continental rise. This is the vertical scale is greatly expanded. And the sedimentary rocks go down many kilometers in many spots, up to 20, 25 kilometers in some spots along the continental margin, sedimentary rocks. Now, the interesting thing about the continental shelf is that Lester King, again, in this book, provocative book, says that there's a problem explaining these from slow deposition over millions of years because the shelf is too wide and towards the outer edge too deep. That's the continental slope, to have been controlled by normal wind-generated waves of the ocean surface. It's the waves that spread out the sediments, but you should have a slope like this. Instead, you have one that goes way out there at a very shallow depth and then drops off. It's a very unique profile, which I think can be accounted for by the runoff of the Genesis flood. So the summary of the sheet erosion by wide currents, maybe 2,000 kilometers wide and maybe a couple of kilometers deep, our continental erosion remnants are evidence for rapid sheet erosion. The continental shelves provide evidence for rapid sheet deposition along the edges of the continents and not slow processes over millions of years. So now that's the preliminary. Now we can get into some of the landforms, as they call them. A landform is essentially the form of the land, the shape of the land, like a mountain, valley, maybe a cut through the mountains called a water gap I'll talk about, or maybe a flat surface called a plain or a plateau or a prairie. These are what's called landforms. So I'm only going to talk about one sheet flow landform and one channelized flow. So I'm going to talk about erosion and planation surfaces, but let's define what we mean here. The flood can be divided up into a flooding stage and a retreating stage. It's like any flood, a river flood or a flash flood. The water goes up, reaches a peak, and then it goes down. And that's what the Genesis flood was over 371 days. And so the peak was probably around day 150 when the ark grounded and the fountains of the deep and the windows were closed. And then the waters ran off. And so you had two phases, phase 4 and phase 5. Phase 4 was when you had few mountains to block the water, the currents were very wide and thin. So it has the consistency of a sheet when you're looking at a sheet. So that's called sheet flow. Well, but then when more mountains and plateaus come up above the floodwaters go around these features and become more channelized, and that's where you carve out valleys and other features very rapidly. And that would be in phase 5, near the very end of the flood, right in there. So you have two phases. So I'm going to talk about one landform formed during stage 4, the sheet flow phase, and one during the channelized flow phase. So the first one is planation surface, or erosion surface. What is an erosion surface? Well, the dictionary of geological terms says it's a land surface shaped and subdued by the action of erosion. That's really not too provocative, but I mean, it's by erosion, especially by running water. Now that's very significant because they've actually say that running water has carved the whole surface of the earth. And one of the reasons why they say that is a lot of times on these erosion and planation surfaces, you have rounded rocks from the action of water. Call them river rocks, if you will. They're not rivers, though. It's from wide currents in this case. The term is generally applied to a nearly level or nearly level surface. If the surface is really flat, it's called a planation surface. It's flat as a plane. If it's kind of rolling, it's called an erosion surface. So let's take a look at one right here. This is in the Bighorn Basin. This is that basin where I made that calculation of the amount of uplift of the granite crust. You can see dipping sedimentary rocks like here, dipping to the west about 50 degrees to 30 degrees, right in here. But something is sheared off that flat. This is probably a dome that went up like this, and some mechanism flattened it out. Now, you don't see things like this happening today, except locally around a river that floods and goes out of its bank. It will flatten some sedimentary rocks, but it's only local. You don't see these large-scale planation surfaces forming today. But whatever formed this sheared everything, soft and hard rocks the same, and it left a thin layer of rounded rocks. I'm on the other side here, and you can see some of the rounded rocks on this. It continues where I'm standing here with a valley that carved through it afterwards. This planation surface is actually widespread in the northern Bighorn Basin. So it's actually very large, even though it's been dissected by this channeled right in here where a river flows. So that's a planation surface. So let's take a look at some of them around where I live in northern Montana and Canada. This is Alberta, Canada. This is Saskatchewan, Canada. And here's this whole area in here, which you could see the scale in kilometers. It's a 100-kilometer scale. So from here to here is about 1,000 kilometers. So this is large scale. And there's 4 planation surfaces in here, but this is a plot of only the top 2. This is the top one right here, the Cypress Hills planation surface, which I'll show you some pictures. And this is about, I'd say, 4,000 square kilometers in area. It's been dissected by glacial rivers that broke through and eroded part of it. This in here are a series of plateaus at the next level called the Flaxville, right in here. So, and then there's other ones lower down, but I'm only showing you the top 2. This is a rose diagram for the rounded rocks on the top of the Cypress Hills that show they came from this direction right in here. And they're capped by a special type of rock called quartzite, a metamorphic sandstone that does not outcrop anywhere in this area, but outcrops way down over in central Idaho. So it's been transported and ended up in the tops of these plateaus. All these plateaus are capped by rounded quartzite rocks, transported hundreds of kilometers, sometimes over 1,000 kilometers from their source in the western Rocky Mountains. So here's a picture of the Cypress Hills. Notice how flat that is. That's a planation surface. And it's part of one that's about 4,000, was originally 4,000 square kilometers in size. Now erosion processes today do not form planation surfaces. This is the main point. They erode them. They're being destroyed by present-day processes. But they exist all over the earth, like this. They're so flat you probably don't notice them too much. And here it is in the central part of the Cypress Hills, still flat. This is an erosional scour, I believe caused by glacial rivers, because I find all kinds of big, huge, erratic boulders from the Canadian Shield in here that indicate that Ice Age rivers eroded that out. And on the eastern part, you still see the flat surface up there in Saskatchewan. So, and when you drive up to it, it's as flat as a pancake. And when you drive to the north edge, you see what's capping it, rounded rocks, quartzites, 95% rounded quartzites by water action. And this is 300 meters down to the next planation surface. So this is a high plateau of rounded rocks capping the top of that. And here's what they look like, the rounded quartzite rocks. Here's another more close-up. They're cemented together to form a conglomerate. Now, there's a whole story about these rocks, which I haven't got time to get into. They have this. Remember, this is one of the hardest rocks in the world. It's recrystallized sandstone. Fill up the pores. It's non-porous, and it has these semicircular cracks called percussion marks, which indicates high-powered banging together and turbulence. A lot more than current flash floods today. Here's the big picture. You had a current of water flowing off the Rocky Mountains out onto the high plains around the Cypress Hills. The larger rocks were moving in the bottom and were planing the rough land down to a flat surface. And then medium to smaller rocks are carried up into the flow for a while and then come crashing down. This is how we believe the percussion marks were formed. But because of these, you can estimate the current velocity by various means. And my friend Peter Klevberg in Great Falls, Montana, estimated these velocities and depths for these are minimums for the various types of rocks and shapes. This one is about 100 kilometers per hour for current velocity, and a minimum depth of about, about 60 meters. These are minimums. So what's the big picture? We're talking about floodwaters eroding the Rocky Mountains that are coming up out of the floodwaters and carrying the resistance rocks hundreds up to over 1,000 kilometers downstream and laying them and then eroding them again, and then so that they lie on flat plateaus that are very high currently. With currents, that speed is around 2 to 3 times the fastest flash floods on Earth. We're talking about powerful currents sweeping across the uplifting western Rockies and planing the land flat, forming planation surfaces. Now, Lester King, who's to study these all over the Earth, says these planation surfaces were once much larger because they've been eroded. A lot of them have been eroded. He noticed the words he uses in the same book. I'm quoting from the same book. Very provocative book. A planation of extraordinary smoothness. Notice the terminology he uses. Developed over enormous areas in all the continents. They're on all the continents. From it, most of the world's present scenery has subsequently been carved by renewed erosion. In other words, a lot of it's been eroded. But we know that they were once very large, and they're on all continents and very flat. That's the point. And here's one in Australia. This is actually more rolling. This is vertical sedimentary rocks right in here. It represents a dome that went way up in the air and it's been sheared flat, forming an erosion surface in eastern Australia. This is about, it's called the tableland. It's about at least 3,000 kilometers north-south and maybe about 100 kilometers east-west. It's a huge area, but there's many of these across the Earth. Now, what you do observe on planation surfaces is they're being eroded today. They're being destroyed. They're not being formed except locally around a river during flood. Here's a planation surface in north-central Montana right here, and it's being destroyed and eroded by streams coming out of what's called the Little Rocky Mountains. So we witness them being destroyed, not forming. So here's a summary schematic. If we had slow erosion over millions of years with dipping sedimentary rocks, which are composed of both hard sedimentary layers and soft sedimentary layers, the hard sedimentary layers would be eroded least and would be ridges, while the soft sedimentary rocks would be eroded into valleys. We should see this everywhere. But we commonly see this, where both hard and soft layers are sheared off at the same angle, both hard and soft, leaving rounded boulders on top. That's a planation surface that is not forming today and is powerful evidence for the runoff of the floodwaters off the rising continents. In summary, planation surfaces are not forming today. They're being destroyed. They were once much larger. They're common as erosional remnants. They're worldwide. And they're difficult to explain by the secular model of slow processes over millions of years. They're powerful evidence for the flood. Now I'm going to talk about the first channelized flow landform and the last. There's a lot more I can talk about, but I'm going to talk about water and wind gaps. Now, you got to remember in phase 4 of the flood, you had wide currents. But as more mountains rose and plateaus rose above the floodwaters, it forced the water to channelize around these objects. So the water becomes more channelized near the end of the flood. And when it's channelized, it marks the land, erodes the land in certain ways, in certain patterns that we can see today. And one of them that is quite mysterious to the secular scientists are water and wind gaps, which can be rapidly carved by flow perpendicular to mountains, ridges, and plateaus. So we're down in here, phase 5. A lot of mountains and plateaus are exposed above the floodwaters. The floodwaters are channelized, and they're carving valleys rapidly, and they're forming unique features, other ones of which water and wind gaps are just one of them. So here's a picture of, this is the Bighorn Basin again, and I'm looking west towards Yellowstone Park, which you can't see over there, but right along the edge of the plains you had a mountain range lift up called the Rattlesnake Mountains. It's composed of granite. You can see the dipping sedimentary rocks. This is near Cody, Wyoming, in north central Wyoming. And there's a gorge through here. That gorge is about 800 meters deep. So the Shoshone River that starts in southeast Yellowstone Park flows eastward and right through here, when it could have went around here on a very low area around here and out this way, but it didn't. It appears like it ran up the mountain and down to erode that gorge. These are called water gaps because water is going through the gorge. These are mysteries of earth science. Even though they have about 4 or 5 ideas to try to account for them, they are hard to demonstrate. Here is a close-up of it as you're going into the gorge. And as you pass through, you see where they made a reservoir here, and it's over here on the left is the water gap. But here's the part where it could have gone out to the south in a low area. In fact, they had to make a dam there to keep the water from going out in this reservoir. So it's so low. So why didn't the river go there originally when the sediments were a little higher in that valley? Instead, it cut right through the mountain. It appears to cut through the mountain. Well, rivers don't cut through mountains, so what's going on? Well, they don't know. They have some ideas that they mention, but they really can't prove any of these, and there's actually evidence against many of them. Now here's a water gap right here on the Susquehanna River in Pennsylvania in the northeast United States. This is one of 4 water gaps. You can't see them back in the next ridge. This is a series of ridges with these gaps through here. In the whole Appalachian Mountains, there's 1,700 water gaps where the river goes through the ridges when it could have easily gone around the ridges. Why did that happen? There's also a lot of wind gaps. Now, what's a wind gap? Well, it's kind of like a water gap, but it didn't quite erode deep enough for water to go through it, so only wind goes through it. This is the Cumberland wind gap. When the pioneers that settled the eastern United States moved west, they went through this. The sedimentary rocks, you could see the sedimentary rocks here, the Appalachian Mountains, used to be like this. And something carved a V shape there, but wasn't deep enough down here for water to go through. It's a pass. It's a high area, so only wind goes through it. That's why it's called a wind gap. So water and wind gaps are big problems for secular scientists. And there's thousands of them across the earth. Some of the most entertaining ones are in the Zagros Mountains of Iran, western Iran. A guy named Thomas Oberlander did his PhD thesis and wrote a book called The Zagros Streams in 1965. Notice how he describes the drainage patterns of these rivers. The rivers don't go down valleys like they're supposed to. They more commonly go through mountains and sometimes come back out. They do really strange things from a secular point of view. Here's a quote from 2 pages. The Zagros drainage pattern is distinctive by virtue of its disregard of major geological obstructions, both on a general scale and detail. In other words, it goes right through barriers where it shouldn't. Now, certain streams ignore structure, that's geological structure, completely. Some appear to seek, I really like his adjective, seek obstacles to transect, as if the river had a mind and said, I want to climb that mountain and break through it, instead of going down through the valley. But anyway, the deepest water gap in the Zagros Mountains is about 8,000 feet. That's about 2,500 meters deep. And there's, about 600 or so water gaps, at least in the Zagros Mountains. So there's thousands of them across the earth. So I'm just going to summarize. I can go through and the secular hypothesis and show their problems. I don't have time. I've published this information, and I'm going to publish more in the future. But this is how I believe they occurred during the flood. Remember, we're talking about floodwaters going down and land coming up. So in the first block diagram, we have water going perpendicular across a ridge. And ridges generally aren't flat, there's low spots. And the water will tend to want to flow through the low areas. And when it does that, it'll carve out a gorge rapidly and will channelize the water through here and through here. And as this process continues, it's flowing at high speeds, carving this gorge rapidly, and same over here. But for some reason, this gives up, and all the water eventually goes through here, leaving this high and dry as a wind gap, and this as a water gap, as I show you right here. So the rivers will naturally go through the mountains in the water gap, but these higher ones are wind gaps. So that's how the flood, draining of the floodwaters, channelizing, can form these water and wind gaps rapidly, and we have thousands of them across the earth. So in summary, major features of the Earth's surface can readily be explained by the retreating stage of the flood. Massive erosion leaves behind tall erosional remnants like Devil's Tower, planation surfaces, and long transported boulders, which I didn't tell you much about. That's the quartzite boulders. The eroded sediments form the continental shelf. Channelized erosion cuts water and wind gaps. Therefore, there is abundant evidence that receding water from Noah's flood shaped the Earth's surface. Mainstream geologists have great difficulty explaining all these features with their slow processes over millions of years model. That's what's called uniformitarianism in the technical geological jargon. All these features are worldwide, indicating a local flood? No, a global flood, not a local flood. This supports one of the most mocked historical accounts in the Bible, namely the flood. And if the flood is a real event, we can easily trust the spiritual aspects of the Bible. We can trust the whole Bible. So if you want to know more about this, this is a summary called not only about planation surfaces and water and wind gaps, but other topics of geomorphology. You can get the information in this book, Flood by Design. This is the real title. Master Books, they wanted that title. I'm not wild about it, but I guess it's more pizzazz. Anyway, receding water shapes the Earth's surface. So you can get that online. I'd be surprised if they have it here. I and my daughter, Tara Wolf, and an artist just wrote this book. It's a geology book for young people, but it's good for adults too. It's called Exploring Geology with Mr. Hibb. Now, it's geology that especially has affected Western culture, starting with what's called the Enlightenment, quote unquote, in the 1700s. It was geology. And from geology, they looked at features on the surface of the earth and said, oh, this has to take millions of years. So practically overnight, the earth became old in their minds. So the millions of years came into it. And what they do now is they find evidence to support the millions of years while they ignore evidence that does not support it. So this book presents geology from a biblical point of view and deals with the millions of years at a young age, all the way down to grade 3, ages 9, in a cartoon fashion, a fun fashion geology from a biblical point of view. So that's all I want to talk about, and that's the end of my talk. Thank you.